In this video, we'll have an introduction to how an automated visual field test works. So, in order to test peripheral vision, in the clinic, we're forced to use confrontational testing. This is what we learned as medical students to do, where we have the patient look at us, focus on our target, such as our nose, and we test their peripheral vision by asking them to count the number of fingers that we present to them in various quadrants of their visual field. And as you can imagine, this test is very coarse and certainly can miss many important visual field defects. So for much more sensitive testing, we can use machines which give us much more detailed information. And this is an example of one machine that we use in our clinic at Hadassah called the Humphrey Visual Field Analyzer, and I'm going to focus my talk around it. So here is a typical visual field that you might be confronted with, and my goal is to give you a little bit of comfort in terms of navigating your way around this visual field and understanding what you're seeing. So let's pretend now that we're a patient taking the visual field test. And what you're looking at here, that yellow light, is a fixation light that's at the back of the machine. This is the light that you're told to focus on the entire time while you're doing the test. And as the test proceeds, at each of these locations marked by an X, your sensitivity to light is going to be tested. Of course, we're going to test each eye alone, so let's pretend that you're patching your left eye in this test and that your right eye is being tested. And the machine tests your peripheral vision that extends basically 24 degrees from the site that you're focusing on. 24 degrees to the right in this case, to the left, up and down. As you might notice, it tests a little bit more towards your nasal side. And that's because these points over here, this region, is particularly sensitive at detecting glaucoma. So it is important to point out that if you think about it, 24 degrees is not very much of our peripheral vision. For example, if you, while you're closing your left eye and you look straight ahead at something, think about how far out to your right you can see with your right eye. You'll notice that you can see well beyond 90 degrees. You probably can see about easily 60 to 70 degrees upward and downward, and maybe a little bit less on the nasal side where your nose is blocking your vision. But the important thing that I want you to realize is that when we're testing 24 degrees, we're not testing very much of the peripheral visual field. We're testing the central part of the peripheral visual field. And that certainly has implications because it is possible that you could have a patient that says that I'm not seeing in my peripheral vision, and that if we send them for this test, the test could come back completely normal, and yet the patient absolutely has something wrong. So it is one limitation that we need to bear in mind. Let's continue. What we're going to do is now do a simulation where we would experience what would be involved in testing this particular location that we've circled at this particular X point. So the test begins, and what happens is that you'd be holding a little clicker in your hand and told to click the light every time you detect that the light is present. So a light comes on for a moment and then goes away. And in this case, imagine you saw it and you would click your mouse, the mouse button that you indicated to the machine that you knew that the stimulus was there. The test continues, and now a fainter light appears and disappears, and probably you still saw it, so you would click, telling the machine again, you still see a light that's a little bit fainter. And then a light there appeared and disappeared, and I imagine most of you watching the video would notice the light was there. Let's just imagine at that point that now it's too faint for the patient to actually see, and they don't click, there's no response. So the machine says perhaps at that location, that's the limit of the sensitivity to light at that point. And so it makes the stimulus a little bit brighter again, and this time there is a click. And based on that, the machine has an idea of how sensitive your eye is to light at that location, and it gives it a score. This score is in decibels of light. That's beyond the scope of the presentation, but let's just assume that your score there would be 10. Now the machine has tested this particular location, and now must go on to test all the other locations shown here. So the test does take a while, and as you can imagine, can be quite boring for the patient. After the test is completed, we have the values. And so here we have the 10 that was assessed in our example, and the other values here, where we have scores for each. The higher the score is, the better the patient's sensitivity to light was. So a 32 would be pretty good, whereas a 7 would be pretty bad. And the fact here, this, in this case, is a less than 0. What that means is that the machine stimulated with the brightest possible light that it uses to test vision, and even there the patient did not see, and therefore their score is less than 0. Whereas a 0 over here on the side would mean that just there the patient was able to detect the brightest light that the patient could see. So again, there's an inverse relationship here where the higher the score is, that means the dimmer the light that the patient was able to see. Then again, the higher the score, the better the vision is in that particular location. I'd like to point out that in a normal visual field, we tend to see the values increase as you move from the periphery to the center. So here we start off with 20, it moves up to 23, 25, 30, 32. This is what tends, or what should tend to happen. Here again, moving from the periphery down at the bottom, upward we go from 27 to 30, and we get up to 32. Here it didn't quite go up, but that should tend to be the pattern that we're always looking for. That the values, the closer you are towards the center, where your fovea is, where the center of your fixation is, the more sensitive to light your retina tends to be in general. And we may come back to this later, but this is what's known as the hill of vision. The hill is formed by the fact that as you move out from the periphery to the center, if you were plotting out the sensitivity to light, you would see that it continuously rises as you move towards the center of the vision. So obviously, for a clinician to sit and read through all these numbers is a little bit cumbersome. So the machine does a statistical analysis, and of all the points, and presents this graph, or this picture here, which is called a pattern deviation plot. And it's doing a statistical analysis, and we're all familiar that this would be a statistically significant p-value, a p-value that's less than 0.5%. And so points that are abnormal enough that there's a high confidence that they're abnormal beyond 0.5% are marked with a black square here. These other points here, such as here, have a p-value that is perhaps concerning, but it hasn't reached statistical significance yet. The machine then, because even this is a little challenging for some people to look at, gives a more pleasing representation of the pattern deviation in something called a grayscale map. What's important to point out is that there's extrapolation that's occurring here. Obviously not all these points were tested, only these points were tested, and this is really the true scientific data that one should look at. this grayscale map is probably something that's more easy to show to patients. Okay, so now we come back to our printouts, and I hope that at this point you can have some familiarity with what's gone on here. The test started out by gathering, after the testing, these values here. We're not going to focus on what's going on here, but just to understand over here, a pattern plot was generated from this data to show us what points are statistically significantly abnormal. And this grayscale map is a representation of this map in extrapolation, giving us a sense of what the patient's visual field was at these particular points. So, medical student, when you look at this particular patient's visual field, can you identify the pattern? Well, we'll come back to that in the next presentation.